Bismillahirrahmanirrahim. Hello, dear students. Today we focus in the chapter 14. 40. The purpose of this chapter is about the principles of the gas exchange and diffusion of the oxygen and the carbon dioxide through the respiratory membrane. We mentioned before, and after the alveoli are ventilated with the fresh air, uh, and they expect the next step in respiration is diffusion of oxygen from the alveoli to the pulmonary blood, and diffusion of the carbon dioxide in the opposite direction out of the blood into the alveoli. The opposite direction there is between oxygen and CO2. The process of diffusion is simply the random motion of the molecules in all directions through the respiratory uh, membrane and adjacent fluids. However, in the respiratory physiology, where we are concerned not only with the basic mechanism by which diffusion occurs, but also with the rate at which it occurs, which is the much more complex issue, requiring a deeper understanding of the physics of the diffusion and gas exchange. For the general consideration, you should know here the dynamic movement of the gas depends on gas partial pressure, and that is to say, driving force for gas movement is different in the partial pressure. Another point in this here we should be mentioned physical diffusion and amount of the blood flow influence at the amount of the gas in the blood. Respiratory gases diffusion from the areas of the high partial pressure to area of the low partial pressure, okay? And the rate of the diffusion of the respiratory gases, for example, for oxygen, nitrogen, and carbon dioxide is directly proportional to the pressure causes by each gas alone, which is called the partial pressure of the gas. What means the partial pressures? Partial pressures are used to express the concentration of the gases, because it is the pressures that cause the gases to move via the fusion from one part of the body to another. The partial pressure of oxygen and carbon dioxide and nitrogen are designated PO2, PCO2, and PN2 respectively. According to the Boyle's law, gas pressure in the closed container is inversely proportional to volume of the container. We have this equation P equal with the nRT to V. Okay, P is equal with the reversible with the V. In this figure, you can see in this here, for example, the closed container with which gives the number of the gas molecules, okay? And this here you can see volume is very low and pressure is high, and this is the piston, and this is the pressure recorder. At this to this figure, you can see volume will be increased in comparison with this one, and the pressure will be low in this case with this. Another figure, in the final figure, you can see the volume is very high, and molecule of the gas is the concentration is low, and pressure is between low. Okay, this pressure low and volume high. This pressure high, volume low. The physics of the gas diffusion and gas partial pressure, molecular basis of the gas diffusion, you can see in this here, diffusion of oxygen from one end of the chamber, from A to the another B. And the difference between the length of the arrows represents net diffusion. Net diffusion of the gas in the one direction is very important. An effect of this concentration gradient is related to the net diffusion. Based on the figures we mentioned before, this figure, and you can see the net diffusion of the gas in one direction, effect of the concentration gradient is very important. If a gas chamber of the or a solution has a high concentration of the partial gas at the end of the chamber and a low concentration at the other ends, as shown in the figure, this figure. The net diffusion of the gas will occur from the high concentration area towards the low concentration area. The reason is obvious. There are far more molecules at the end of this chamber to diffuse toward the end of NB in this here. There are molecules to diffuse in the opposite direction. Therefore, the rates of the diffusion in each of the two directions are proportionately different, as demonstrated by the length of the arrows in the figure. The gas pressure in the mixture of gas is a partial pressures of the individual gases. The respiratory physiology, one deals with the mixture of the gases, mainly oxygen, nitrogen, and carbon dioxide. The rate of the diffusion of these gases is directly proportional to the pressure caused by that gas alone, which is called the partial pressure of the gas. The concept of the partial pressure can be explained as follows. Partial pressure of the gas is calculated by the multiplying its fractional concentration by the total pressure exerted by all gases. Therefore, the partial pressure, for example, for the oxygen is the 21% of the atmosphere, and 760 millimeter mercury, and multiplied to the 0.21 means 160 millimeter mercury for pressure oxygen. This mixes with old air already in the alveolus to arrive the PO2 of the 104 or 5 millimeter mercury. For the carbon dioxide, the pressure in the atmosphere is very low, partial pressure, okay, and less than 1%. And this mix, which shows in the atmosphere, we have a 0.3 millimeter mercury for the CO2, pressure CO2. You can see the pressure oxygen atmosphere is high, and pressure the CO2 in the atmosphere is very low. This mixes with the high CO2 levels from the residual volumes in the alveoli to arrive at the pressure CO2 of the 40 millimeter mercury. You remember two pressure in the alveolus and the alveoli in the respiration system. CO2 is the 40 millimeter mercury, and oxygen is 104. Air has a composition of the about 79% nitrogen and about 21% oxygen. Total pressure at the sea level, atmospheric pressure, average 760 millimeter mercury. Therefore, 79 of the 760 millimeter is caused by the nitrogen and 600, and 21% by the oxygen. And the partial pressure of nitrogen in the mixture is 600, and the partial pressure oxygen is 160 millimeter mercury. The total pressure is 760 millimeter mercury, the sum of the individual partial pressure. You can see in this figure the air 79% nitrogen, 21% oxygen, total pressure 760 millimeter mercury. Partial pressure is related to this here we mentioned before for the nitrogen and oxygen. Based on the Dalton's law, every gas in the mixture of gas exerts a partial pressure equal to the pressure it would exert if it existed alone in the same volume. The total pressure is equal to the sum of the partial pressure, and P total equal P1, P2, and Pn. The pressures of the gases dissolved in the water and tissue is the same with the other in the gas phases. The partial pressures of the partial separated dissolved gases are designated the same as the partial pressures in the gas state, okay, and that is the PO2, PCO2, PN2, and P helium, and so forth, okay. And the factors that determine the partial pressure of the gas dissolved in the fluid. These factors related partial pressure to concentration, and solubility coefficient of the gas. Two factors is involved, main factors about the partial pressure. And the relation between gas concentration and gas solubility is determining by the partial pressure of the gas is expressed by Henry's law. In base of this law, partial pressure equal the concentration of the dissolved gas and with the solution